start today's discussion. So the plan for today is that I'm going to spend the first hour, first a review on our discussion on Miller effect and Miller approximation. And the next part is then we're going to talk about parasitic capacitance in transistors and how are these parasitic capacitance are being affected depending on its operation condition or how, the size of your transistors, and how does it determine the bandwidth of a certain technology. So we're going to talk about that. That's probably the main two topics hopefully we'll be able to address today. So we're going to go back to what we have already, sort of a little review on what we have been talking about last week, which is Miller theorem or Miller approximation. So the basic idea is that when we talk about frequency response, typically what you're concerned with is mostly how fast can a particular circuit node move. So the key component is that you want to understand how much baggage you're carrying. The basic idea is that what is how fast can this particular node move will depend on what is the effective capacitance being seen at this particular node. So we're going to talk about single time constant. When we actually discuss circuits, we're going to talk about how do you address zeros and poles. How do you find mostly poles based on node analysis on capacitance. So because of that, therefore, you need to understand the effective capacitance being seen at each particular node. So that is why we want to look at a particular case. If you have a capacitance which is referenced to ground, that's the most easily way to understand when you're filling. For example, if you have a tank, it's placed under the ground. The bottom is on the ground. Therefore, when you fill it, you can then observe the rise of potential, rise of water level based on the amount of current being pulling in. That's the response of a capacitance. But so we're going to talk about a very special case of capacitance, which is that it's not placed in reference to ground. So when it's not placed in reference to ground, that means that the opposite terminal can move as a response of V1 as well. So this is when Miller effect is when V2 equals to minus A, 0 V1. So V2 can respond to V1. So when you try to fill up your tank at this terminal, you want to see, you try to drive up terminal 1. What happens is that the opposite terminal actually falls down if you have a inverting amplifier. So what happens is that you need to put in more water in order for the potential to rise at potential V1. That is the main reason you see a particular drag on terminal 1. Therefore, it's very hard to drive it up. So how do we explain these things without having to analyze this cross-coupled interference? Is to introduce something called effective capacitance. So you want to make all your capacitance relative to grounds to make this analysis easier. So what we do is that we establish this equivalent. This is the equivalent model with C1, C2. These are, as I said, these are equivalent capacitance. So C1, C2 as equivalent caps. These equivalent capacitance, how does one determine, how do you use a C1 to represent the hard to drag point of terminal 1? Is by we use our derivation on equivalency in terms of the response of voltage current at voltage terminal 1 and terminal 2. So the equivalent capacitance is that, as we already seen, if you have a non-inverting, in an inverting amplifier, what happens is that C1 will be typically amplified by a factor of 1 plus A0. So this can be relatively significant because you would then have this simply means that this point is very hard to drag up. The main reason is because terminal 2 is going to the opposite direction. Therefore, you need to put in more current in order for the potential to rise. That's the same as having a large capacitance. And you will see that C2 will experience somewhat increase of capacitance, but it's not very significant because it's 1 over A0. Typically, A0 is a high number, then it will be very close to 1. So in typical case, let's say if A0 is much larger than 1, then what happens is that you would then have a enhanced large. The reason is that you would then have large C1, and your C2 will be approximately CF, if that's the case. Another scenario is that if you may have these feed-forward capacitance in between non-inverting amplifiers. So if you think about it, and we're actually not going to go through examples with non-inverting component, but you can see what may happen. So if there's a case if A0 is smaller than it's negative, I should say it's negative. So what happened is minus A0 is larger than 1, larger than 0. That means that it's a non-inverting. If you have feed-forward capacitance in the non-inverting amplifier, so what typically would happen if you have that is that you may have two problems. One is that if A1 is, let's say, there's two conditions. If A1, the value of minus A1, the non-inverting component, I should say, let me just use A1. A1 is negative. Simply means that non-inverting, meaning that the gain itself it's negative. I should say A0 is negative, but minus A0 is positive. So if minus A0, the overall gain, this is a positive number, is smaller than 1, you would then have smaller. So this is when the opposite side is lifting as you're moving upwards. So this is like if you have a source follower. What happens is that I'm trying to, this will follow this. If this one is, let's say, a gain of 0.8, so that you don't need to actually feed that much current. So you would then see effectively much smaller C1. And, okay? So the other thing is that the other thing may happen if you have, that's only look at as C1. So if this is larger than 1, then you would then have a negative capacitance. So this is not a real negative capacitance, but this is effectively being built up through circuits. So sometimes if you want to have some oscillating effect, you want to probably build negative capacitance. So this can be deliberately used in oscillation circuits in order to build negative capacitance for certain filter applications. Okay, so you can deliberately make negative capacitance out of these type of architecture. But mainly we're going to focus ourselves on applying this theorem in inverting amplifier. And this is the most significant part, is that if you have feed-forward capacitance across an inverting amplifier, that will lead to lag. In reducing capacitance, in most cases when we discuss the circuit, its bandwidth, typically what you look for is the slowest node. So the slowest node meaning largest capacitance, which has the highest baggage. So it's like in a relay run, you look for the ones that runs the slowest. This is the same for circuits. So in terms of discussing bandwidth, not for oscillating or other applications, you look for nodes with largest capacitance, and that will happen only when feed-forward capacitance are connecting between inverting amplifier, okay? So I want to emphasize again to evaluate, as I said, to evaluate the bandwidth of a circuit. We're going to talk about that so typically what we do is that we look for the slowest the node that moves the slowest node will then determine by two things. One, slowest nodes will correspond to what we call determined by the lowest frequency poles. So it would be governed by the lowest frequency pole. These lowest frequency poles are typically referred to as the dominant As we already discussed, most of the poles are determined, if you look at dominant poles, omega p, let's say omega p1 is the dominant pole, it will typically determined by RC. So you look for the largest R, you look for the largest capacitance. As I said, Miller capacitance, the reason why we're concerned about Miller capacitance is because it has significant amplification effect, so it will then introduce a large effective capacitance. So you look for largest cap and highest is typically referred to high impedance or high resistance node. Typically, when you talk resistance node, you look for nodes that, the way to think about this is that if you have a node that's moved most slower, the slowest of the, if I have like 10 nodes along the circuit, how do I find the slowest point? The slowest point will depend on, it will have the largest baggage, meaning that it has large capacitance associated with that node. The other thing is that it has very little charging power, meaning that it has low current to charge up the node. Simply means that it has high resistance, therefore the charging current will be limited by these resistance, okay? So the resistance will limit the amount of charging current. The charging current will limit by resistance, and the capacitance is your baggage. So the larger the baggage, the larger your tank, the slower it will respond under the same amount of charging current. Okay, so the reason why we're looking for large capacitance is because that will determine my overall bandwidth. So let's go through an example so you get a sense as to what, how does one analyze this type of, when circuit experience Miller effect. So these are typical problems you need to be able to answer. So I'm just going to give a, let's say if I have a 1 picofarad CF, a feed-forward capacitance, and then my input terminal might experience its own, it already has some input capacitance Cin, and the output terminal will also may experience some loading capacitance. So let's give a number so you get the overall. So this will be equivalent to minus A. I want to determine the overall capacitance as C1. So you need to add the original parasitic, the overall capacitance. We need to determine to find C1 and C2. So the question is that to find these two. Let me give the numbers. So at the beginning, I have input capacitance, which is 1 pico. And I have loading capacitance, which is also 1 pico. So 3 of them are both 1 pico. After this voltage gain, I have A0. Let me give the parameters. So if I have a circuit with a feed-forward of 1 pico, input output are the same loading, and then A0, a gain of modest gain of 10. So you need to find out what C1 and C2 are. So first of all, we use Miller approximation, so we know that C1 is supposed to be C input plus the Miller approximated amplification, that's A0. That's equivalent by Miller approximation. So let me just use another label. This means, let's say node X and node Y. So that it won't get, the C1, C2 will not be confused by. So we want to find the capacitance, loading capacitance on terminal X and Y. On node X and Y, as I said, we want to use this to find poles at node and X and Y. That would be CX and CY. So this will be equivalent to CX, CY. Okay? So if that's the case, these are X and Y, just to be clear. So this will be, let me rewrite this. So the equation will be based on Miller approximation. It's supposed to be CX should be its original input capacitance plus C1. And that's C in 1 plus A0 times CF. So this will give me 12 picofarad. This will give me 11 plus 1. And CY will then be C load plus C2. C2 is based on Miller approximation, so this will be C in, C load. 1 plus A0 CF. So this is 1 plus 1.1 pico. That will give me 2.1 pico. So this will be 12. And then the latter will be 2.1. Okay? So finding out the loading at each terminal is critical in the next point when we want to find which one is the dominant poles, which ones are the higher frequency poles. So, okay? So I'm gonna go through another example before we start talking about transistor parasitic capacitance. I'm gonna use another example where Miller effect will help, Miller approximation will allow us to find poles. You need to find your poles and transfer function, to draw transfer function. So example of a common source amplifier. So for a common source amplifier, it looks something like this. I have a loading of M1, RD, VDD. And then I will have a source resistance. And there'll be a feed-forward capacitance between the two. I add a feed-forward capacitance between the two. So let me give parameters. So this will be my input terminal, V in. This will then be the output terminal. So let's give a few device parameters. First of all, this M1 has a GM, it's being biased as a GM1 of 1 milliamp volt squared. A volt, sorry. And then my RS is 10K ohm. RD is 20K ohm. And then we'll have a CF. The added V4 capacitance is at 0.1 picofarad. A relatively small V4 capacitance being connected between the two. So basically what happened is that you could view this as an amplification stage. So this can be equivalent to, I'm having this minus A0 CF. This will be my input RS. This will be node X, as we have already followed node Y is the output terminal. So this will be, let me highlight it more clearly. This will be node X. This will be node Y. Okay? And this is connected, the loading of this, you can assume that if you use small signal model, you will see RD at this particular terminal. So the voltage gain, we want to find our low frequency voltage gain. Minus is the gain of this common source stage is minus GM1 RD. So this will then give me a gain of 20, minus 20 volt over O. That is to say A0 equals to 20. Once we have that, we can then reconstruct the circuit by equivalent to this. So you don't really care about what happened within, but then it will be CX, CY, and it would have a loading resistance, RD. What you see in the front will be the resistance of RS. I should probably not use this. This is more like a GM stage, but if you want to do an equivalent, this will more like a GM stage because minus GM1. Because you're driving the loading in parallel, these two loading capacitance in parallel. So that will be my equivalent circuit. This will be Vin. This will be VL. So if you do this, we want to first find out C1 and C2. So C1 will be CF times 1 plus A0. This will give me 2.1 picofarad. And C2 will be CF 1 plus A0 over 1. This will be approximately 0.1 picofarad. So what happens is that we'll then have a pole, which will then, CX, which will be much, much larger than CY. Okay? And then I know RS, this is 10K. And this is 20K. So based on this equivalent circuit, we should be able to construct our transfer function. So the transfer function, the way to do this is then it will be Vx over Vn times Vx Vy. And then so Vx over Vn, you could view it as a high-pass filter, so you get, I should say, low-pass filter, because I have an RC network, so you get 1 plus j omega p1. And then over that will be over 1 for RC, where omega p1 is Rs times Cx over 1. So that will give us the first component. And then the second part will be Gm. As I said, this will be Vx Vin. And Vy Vx will be Gm times, there should be a minus Gm times Rd in parallel j omega Cy. So that will be the second term. This will be Vx Vy because you have capacitance and loading resistance in parallel. If you look at it in a small signal way, so this will be Gm times these two. If you can't see that, you can simply insert the small signal model, and that should become more clear. So this is, let me highlight. So this is the voltage divider part, which will give me this. And Vx and Vy is determined by the loading component. So after arrangement, you get the response, which is minus Gm. Let me write it down and use this. So the overall results, transfer function will be, it's low frequency. This is the low frequency minus A0, which is the low frequency gain. And then you need to consider the effect of two poles, omega p1 plus j omega p2. Okay? Here, omega p1, we already know that omega p1 is determined by Cx, which is the input terminal. So typically referred to as the input pole. Since we only have two terminals, there's input terminal, input pole, and output terminal. And output terminal will give us omega p2, which is determined by Rd Cy over 1. So this is determined by its output terminal. You have an input pole and an output pole. So which one will be the dominant, will be the lowest frequency? So we're going to determine its frequency first. So omega p1, based on the parameters given, omega p1 is Rs Cx. We know that Rx is 10K. Cx is larger capacitance. So this will give me approximately 50 megahertz. And omega p2, because the capacitance, the loading is less, even though its resistance is slightly larger, but the capacitance is much lower. Therefore, you get approximately 500 megahertz. So once we have these, we should be able to do our Bode plot based on this. So if you want to plot the gain, we're only going to look at the gain. The transfer function. So you start with the gain of, I have to highlight this. There's two turning points. This is 50 mega. Omega in unit of radius per second. So you start with 50 meg, and then there's another tenfold is 500 meg. That would then be omega P1. This is omega P2. We have 2 poles. So basically, we start with gain of, that's 20. So this is 20 volt per volt. It's about, I should say 23 dB. If you want to do a dB, you can do calculation. But this is the gain, and then it will start to drop once it hit this. Drop at a rate of, the slope here is minus 20 dB per decade. Let me try not to move so. You start with this, and then you have a slope. And then once we hit another one, it would then become sharper. So you have 2 slopes. One is at this region, you would then experience minus 20. In this region, once it passes 500 megahertz, it will then be 40 dB. Okay? And then this will be, this is typically referred to as the 3 dB frequency. So omega minus 3 dB is determined by omega P2, P1, sorry. Which is referred to as the dominant. This will then determine our 3 dB or omega 3 dB or corner frequency. Even though there's 2 poles, the second pole doesn't have too much effect other than stability issues. When you're not using it in a feedback fashion, if you doing open circuit analysis, what you really care is when it start to drop in terms of decay and gain. Okay? So that would typically determine our open circuit bandwidth of a circuit. Okay? So we'll see that even though you have only one capacitance, because of Miller effect, the input terminal would then experience this Miller amplification. Therefore, you would then see the dominant pole be determined by the input terminal is simply because of Cx is become much, much larger than Cy, even though I'm only inserting only one capacitance. The next thing I would like to start to discuss is that these capacitance, this 1 pico capacitance, typically what we do is that you add it deliberately and use that to set the dominant pole. So if I'm adding this CF, I could actually allow this pole, a large or low frequency pole, without having a large capacitance. That's one of the purpose of having using Miller effect to our advantage. But other cases is that if we're not actually deliberately adding capacitance, but if you're having transistors, they already come with capacitance. These are called parasitic capacitance. So we need to go back and revisit. These are externally added capacitance. But what if, without these CF, the transistor actually come with capacitance, especially for MOSFET? If you think about it, it's a capacitance, it's a parallel plate capacitance built transistor. Therefore, it must have significant capacitance components within the circuit, within the device itself. So we need to go back to the device analysis a little bit to introduce something called a high frequency. And spend a little time to start discussion of what we call the high frequency transistor model. So basically what happened is that before we start, you think about your small signal model, high frequency. So we revisit our small signal first. So without, when you use that low frequency, meaning that you omit all the capacitive component. So small signal model used for low frequency analysis, it looks something like this. For BJT, let's look at BJT. So for a bipolar junction transistor, you have a R pi, which would describe the base current. We have a GM B pi, which will allow us to characterize the effect of control, mostly VBE controlled of collector current. And then you have an RO, which is early effect. Okay, so these are the low frequency small signal model where capacitive components are ignored at the beginning. But if you actually look at the circuit, if you go back to think about the real circuit, this is the base, this is the emitter, and this is the collector. So the device, remember, is operating in active mode. So if we're going back to our NPN, I just assume it's an NPN. So in active mode, what happened is that emitter base collector. So you basically have BE junction, which is forward biased. Remember, this is forward bias. I will then have a lot of electrons. These are electrons QN, and there will be QP on the other side. And then I have depletion on the right-hand side. So this is, so you have BC junction, which is in depletion junction, and this is a forward bias forward. So you have a forward junction. This is the reverse junction, which is junction in reverse. So first of all, before we talk about forward bias is a little bit more complicated. In reverse bias, you think about it, for my BC junction, inactive is in reverse. So therefore, between them, there should be depletion capacitance. So go back to the device, and depletion capacitance is a decrease as we the voltage across the junction increases. So depletion capacitance, you have depletion capacitance, can be written as a junction capacitance at 0 volt, 1 plus V bias. So my bias is VBC. Okay? And typically, if you look at the equation, it should be square root of 2. Remember, BC is negative, therefore the negative sign will then become VBC. Here, VBC is smaller than 0. It's negative. So your equation based on this is unit area typically it's unit area junction capacitance, called the junction capacitance, under 0 bias when VBC equals to 0. Okay, so you have this is typically a given parameters, device parameters, depending on the type of doping that's given between B and C. Anyway, the key of this capacitance is that as VBC, reverse bias, increases, the depletion capacitance actually decreases. Remember, because it's further away, depletion grows further apart, therefore you have smaller capacitance. So this is depletion capacitance. So in this case, we're just going to inject a capacitance. So to include high frequency components between B and C, there's C mu. We call C mu. And C mu is constructed with a C depletion times area of BC junction. So that's unit area, therefore you have to time the area. It depends on the area. And then the other capacitance is between, let's look at BE junction. So in BE junction, if I want to highlight it, it's more complicated. I would then still have depletion. There's a lot more electrons. And there's holes. And then the width, there's a distance between the two. This is WB. So this is the BE junction. If you look at the BE junction, it's actually constructed of two types of capacitance. You have charge, depletion charge. There will also be depletion charge right at the junction. So this will be Na, let me highlight it, Na negative. This will be Nd plus. So you will have depletion capacitance N so basically what happened is, remember this is NP. NPN. So this is the NP region. I'm using an NP region to describe this. So there's two types of charge will then contribute to two capacitance. So if you think about it, this capacitance is referred to BE, the capacitance in a 4-bias BE junction. We're going to call it C pi to be parallel with R pi. So there will be a capacitance between the two. This will be C pi. Okay? So C pi will be constructed with two components. One is, there's two types of charge. This we call, there will still be depletion capacitance, and this depletion capacitance is even higher than that across BC junction because it's 4-bias, therefore the charges are actually closer. You have depletion capacitance which correspond to Na, Nd plus depletion charges. And then we'll have something additional capacitance called a diffusion capacitance. Will depends on Qn, Qp. So where's the Qn? These are the Qns. So typically only look at one side. We're going to talk about that a little bit. So depletion capacitance will actually follow the same equation. So the unit area depletion capacitance here will then be another junction capacitance at 0. This will be a different parameters based on BEJ. So to be precise, this should be BE 0. That will be BC 0. It should be two different parameters. And then this will be 1 minus BE 0. And because BE is 4, therefore you would then have actually a much higher capacitance. And for diffusion capacitance, it would then be determined by so the overall, I should say, there will be diffusion capacitance will then be determined by dq that will be you can only look at one side of the chart. So we want to find out what is Qn as VBE changes. So once I change this voltage across, and you look at the charge, the amount of charge as the Qn. So you want to look at the amount of charge changes for parallel plate capacitance. What we want to do, the capacitance is defined as when voltage change, how much charge, there's a change in charge. So in diffusion capacitor, charge is the electron, minority carrier electrons stored in base. So let's look at Qn. Qn will then depend on emitter area times Q times, let's use the triangle, assuming that there's no recombination. So the triangle, the width is WB, the height is MP, MP at x equals to 0. If you go back to the diffusion component when it's forward bias, so this will simply be triangle 1/2 MP at 0 times WB. Okay? So this equation can be rearranged as Q AEQ 1/2. MP0 based on law of junction is MP0. Exponential. If you've forgotten, can go back to chapter, I believe chapter 4, started discussion of bipolar. So once we have that, we could do some rearrangement. You look at, this is forward bias equation. So what is the collector current? If you go back to review the collector current, IC is AE times Q times DN MP0 divided by WB. If we go back to find the slope and determine this is a diffusion current. I don't actually need this. I'm only referring to this. So I can substitute Qn. The Qn can be rearranged. So based on this is this. So you substitute all these components with IC. So this can be rewritten as IC times a time constant, where tau f, let me try to explain. So if I divide this 2, I divide Qn. Let me rearrange. So I already know Qn is this expression. This is equation 1. This is equation 2. So what if I divide them? Qn, let me write it over here. Qn divided by IC. This will give me 1/2. So it's equation 1 over equation 2. So this will be WB dN 1 over WB. So you simply divide the 2, and then this can be rewritten as 1/2 WB squared over dN. This term is called, this is in a unit of time, so it's called the time constant tau f. So what happened is that we then have a term which is tau f is the size determining on the base width, which is the transistor, the distance between two n regions, how far the minority carrier travels, and then we get our final results, where is Qn equals to IC. Give me about 5 minutes. So once we have this relationship, we can find our diffusion. Remember, we're trying to find diffusion capacitance. So diffusion capacitance C diffusion will then be dQn dVBE. So based on this relationship, it will be tau f is a constant DIC dBE. And this is simply GM tau f. Okay? So let me just try to make some conclusions. So for bipolar junction transistors, there's 2 parasitic capacitance based on this junction. For a 4 bias PN junction, you would then have C pi, which is C depletion times its area, BC junction, BE, a emitter area, times a diffusion capacitance, which is GM tau f. So C pi will be constructed with 2 components, depletion capacitance and diffusion capacitance. In most cases, because this is typically much, much larger than that, so this is typically dominated by GM tau f. Even though there's still some depletion capacitance, but diffusion capacitance typically dominated when determine C pi. So in follow-up assumptions, we're going to assume that, I'm just going to write it over here. We're going to assume that C pi is dominated by you only consider diffusion is because it's much, much higher. It's dominated by diffusion, so it's GM tau f. And C mu will be determined by its depletion capacitance, unit area depletion capacitance times the area of BC junction. Okay? So these are the 2 capacitors being added. I should rewrite this. This is assuming diffusion dominates. Okay? Okay, let's take a break for 10. We'll come back probably 15 after 11, and then we're going to discuss the same high frequency model for for MOSFET. It's actually easier than this because this would diffusion capacitance is a little bit more complicated. Okay, let's continue our discussion. So for a bipolar junction transistor, high frequency small signal model, already established that for low frequency model, you don't need to consider these parasitic capacitance. So we'll look something like this. Emitter, base, collector. Okay? So we'll then have three main components, which is R pi to describe base current, G and V pi to describe transconductance, modulation of collector current, and RO is to describe early effect. So in a more complete model, we'll then have added capacitance. This is C pi, C mu. And then if you want to be more complete, collectors, typically there's also collector and substrate is also in reverse bias. So there's CCS. So I have C mu, CCS. These are reverse bias. So it's a depletion capacitance. It's typically reverse bias junction capacitance. And junction capacitance in reverse are typically referred to as the depletion. So these are depletion cap based on depletion charge, response to depletion charge. Capacitors. Okay, these are depletion capacitance. And then the other part is C mu. As we said, C mu is typically, you can use tau f. It's dominated by diffusion charge, minority diffusion. Minority charge in base. As we said, we use Qn. So where tau f is, as we is a time constant, which is WB squared, diffusion time constant. So we know that this is fixed. This is a constant because this is typically referred to as the transit time. It is the time required for an electron to move from base to emitter within this diffusion region, through diffusion. So you could use it as an average time. For a minority carrier. To move from, to give it a more intuitive sense as to the average time for a minority carrier to move from emitter to collector within base. It's a transit within this transit station, sort of like a transit station. So it's the average time is defined by tau f. So basically what happened is that you can see that the diffusion, as diffusion capacitance dominate, you wanted to have a faster, how does one reduce transit time? Because transit time will then be proportional to capacitance. If we want a small parasitic capacitance, you want to reduce transit time by reducing WB. That's how you increase the speed. So basically to reduce, we're going to talk about bandwidth later, to reduce C pi, the key is to make this smaller by reduce base width, so as to increase the overall speed or bandwidth. of a bipolar technology, a bipolar device. Okay? So once we get that, the next part we're going to look at, of course, the other transistor which is more commonly used, which is the MOSFET counterpart. MOSFET high frequency small signal model. So let's look at the parasitic. As I said, these come with the transistor because for BJT you need to make junctions. For bipolar, for MOSFETs you need to make MOS structure, which is a parallel plate capacitance. So parasitic capacitance. So let's look at parasitic capacitance in a MOS FET. So there are basically two sources of capacitance. One is that you view the capacitance between a cross oxide parallel plate as parallel plate capacitance. Across the dielectric across SiO2 or the dielectric. So this will be between gate. This can happen between gate and source, gate and source, gate and drain, mostly. And then the second type is that because, remember, all of the PN junctions in bipolar junction transistors are in reverse. So it will still have, we call it junction capacitance. Across reverse bias junction. So what are the reverse bias junctions? There's the source to body between, which is between source and body, drain and body. These are reverse bias junctions. So if we plot the schematic cross-sectional structure, so let's assume that I have a P-well. And then this is for simply an N-channel device. I have gate. Get some color. These are the gate. I will then have oxide across. This is SiO2, MOS. And then we'll have junctions. So this will be my N plus junction. And then we'll have a P plus pickup, as we already know that for metal pickup you need to do a plus. So these are the connections. We'll have source, drain, and body for the connections. So if you want to think about what are the capacitance that can occur, So there will be, if you look at parallel plate, this is gate. Mostly is gate. We call this CGC. So there's the C, use small, CGC. Stands for gate, between gate, to channel. But who's connected to the channel will depend on whether it's source or, so there's a channel inversion carrier. So either this is supported by source or supported by gate, depending on its operation condition. So we call it CGC, it's between gate and channel, but where does the channel, the carrier from the channel is being supported will be determined by whether it's continuous channel or discontinuous channel. So mostly CGC, and then there's junction capacitance. This will be CSB. There will be another CDB, right? And these are junction capacitance. So mostly this parallel. This is gate to channel. These are based on parallel plate. And then it will be SB. CDB, these are, we call the junction cap. Okay? So if you think about it, we're constructing our small signal model based on, so let's do the small signal model. So we start with our original low frequency version, which is GM VGS. This is GM VGS. And then I have R out to describe the channel length modulation effect. That's our original small signal model. And we need to add two components. One is between, let me use yellow, gate and drain. So this is CGD. And then there's another between gate and source. So it's not with the fancy names, just follow the gate to source. CGS. So I have gate, terminal, drain, and source. Okay? So of course, this terminal can be extended out with added loading. This typically is the loading capacitance. So this is drain to body. Okay? And of course, if you want to add it to the, this will be your body terminal. Not necessarily ground. For source to body, it can be shorted together, or there's another body. So if you want to highlight it as the body terminal, and this will be SB. A more complete model will look something like this. If you want to include the body terminal, or not necessarily refer to ground, but this is referred to body terminal. Okay? So because this, remember the small signal model is based on the device operating in saturation, so we want to make sure that the MOSFET is operated, MOSFET is in saturation. So in saturation, the channel is pinch off. At the drain side. This means that if I look at a channel, there will be, let me plot it over like this. This would be my N plus region. For an NPN transistor, if you look at the charge, there will be inversion charge electrons. Because this is a discontinuous channel, therefore, your parallel, if you think about a parallel plate capacitance, the charge is coming from gate, the other side is coming from source. So mainly your charge will be CGS. So this is, in saturation, this is discontinuous. So basically, there's only one component that will contribute to CGD. So to think about it, you only have this overlap area. This would then lead to what we call the overlap caps, capacitance. And of course, overlap capacitance will happen in both sides. So there will be another overlap cap on the other side. So first of all, let's describe the overlap. Without the formation of inversion charge, there will be overlap capacitance. So the overlap capacitance is defined by its area. Its area is, let's define the length. So remember, my device looks something like this, right? It's elongated along the side. So this is W. And then I have along the channel, there's 3 distance. This is L, which is the actual distance between the 2 M plus. So it's referred to as the effective length, meaning that it's from M plus to M plus. And then, let me just make sure that I use this. So from here to here, that's L. And then we have this overlap region. If you pull it downwards, the overlap region, there's an overlap distance. So this simply means that the gate, the length of gate extended out into the M plus region is called the overlap length. So this region is defined as overlap length. Once we have this, we can then find the overlap capacitance. The overlap capacitance will simply be the area, which is W times L overlap times unit area capacitance of the left-hand side. So this is also the same. C overlap equals W overlap CX. Because the device is symmetric, so that the overlap is expected to be the same because they are made under the same process. Okay? So that is, we can now know that because channel is pinch off at the drain, so CG, there's no, so this sentence simply implies that no channel charge. Under saturation, channel inversion charge comes from drain, meaning it's discontinuous channel. Therefore, it's not providing charge into the channel. Therefore, your CGD will only compose of the overlap capacitance. CGD is only the overlap capacitance. But for gate to source, there's 2 sources. One is, it also has this overlap contribution, and then plus 2/3 WL effective CX. Okay? So this is from the overlap region. We still have the overlap region. We still have the overlap region, and this is the channel region. We know that it's only connected to the source side, therefore it will contribute to the parallel plate capacitance, which will support the under the channel. This is under the channel. Okay? And the 2/3 is because the 2/3 is the average of it comes from the average of a non-uniform channel, because we know that this inversion channel is non-uniform. Average of non-uniform channel. Okay, good. So once we have these, we can then move on to further analysis as to what is the implication of having these parasitic capacitance. So next is that how does one consider these parasitic capacitance, of course, in circuits? Before that, we need to talk about what we call the transit frequency of a transistor. So once we have this parasitic capacitance, it will actually cast a limit as to how fast can a device or a circuit work, or the speed of the circuit. So it's like intrinsic gain. Intrinsic gain is that when I have the most ideal case, what is when the gain is limited by its channel length modulation effect. So that will then lead to its ultimate gain of the circuit, ultimate ceiling of a particular technology. This is also the same. You talk about intrinsic speed by describing something called the FT, which is the transit frequency of a transistor. So typically referred to as the transit frequency of a transistor, or typically limited by a certain technology, FT. So this is a measure. What's the transit frequency of a measure of intrinsic speed? So it's independent of circuit. It's the speed or the maximum bandwidth it can drive itself in the ultimate speed of a transistor. So it's either called the transit frequency, or sometimes called the cutoff frequency, meaning that after this frequency, then it does not provide amplification effect. So FT is the maximum frequency this transistor can be operating at, which will still provide a certain amount of gain. So how does one test this transit frequency? So you want to make sure that what is an ultimate evaluation of providing a transistor. A transistor should be able to provide current gain, a sizable current gain, in order for it to provide amplification factor. So the FT is typically tested the frequency is defined as the frequency at which, at this particular frequency, it's short circuit current gain. So your current gain falls to unity. So falls to 1. So when does this, at which frequency it will no longer provide current gain. The current gain will be lower than 1, meaning that it does not provide any gain. So the way to test this is this. So this will simply means that for bipolar, what we do is that we use simply a CE stage, because this is where you get the maximum current gain. You inject I in, and short circuit, meaning that you short the output. So to get the maximum, that's your maximum current. So the definition of FT is I out as a function of frequency versus I in as a function of frequency when F equals to FT. It equals to 1. When does it fall to 1? Okay? And this can also, you can do the same testing for MOSFET as well. So the MOSFET test circuit will be something like this. We simply sweep the frequency I in and short circuit output to look at I out. And its definition is the same. You look for at which frequency the gain would then fall to 1. Beyond that, it's no longer an active device. So if this is the case for frequency above FT, it does not provide gain. So gain, your current gain, beta, for MOSFET, for BJT is beta. For beta smaller than 1, meaning that it's no longer active device. For an active device, it needs to provide gain. So it no longer present benefit of present benefit just to be precise. And like an active device, an active device should be effectively providing gain, but falling beyond this frequency, your parasitic capacitance will dominate, bypass the transistor modulation effect. So you won't see the modulation effect. You will only see parasitic capacitance effects. Okay? So let's find out what are the FTs for both devices. So we can simply just do the testing. So we're going to use our small signal model. So we're going to insert, simply in the circuit, we're going to insert our high frequency model. You simply insert the high frequency model and then do the analysis to find out its frequency response. So let's start with the BJT. So remember we had a circuit, small signal model, R pi, C pi, C mu. And then it's a common emitter architecture, so emitters are ground. So we're going to ignore, we're going to only include, we're going to ignore CCS for here. Those are not as critical. So this will be GM V pi. V pi is the voltage across base and emitter. And then we have RO. So external circuit is like this. The testing condition is that I short output. This will be RO. So the circuit is that it's shorted. And then we're going to look for this I out in response to an input sweep of frequency. So you simply generate input as you sweep frequency from 0 to high frequency, and then look for the output response in frequency. Okay? So first of all, let's just based on this equivalent circuit to construct what output current will be. You won't actually see this because we shorted the output. So I out will only be constructed with two current components. One is the transconductance component, which is the effective one that comes from our original low frequency, the main pathway of transduced current to output. And then there is a bridging pathway, which is j omega c mu v pi. So there's current going down. There's two components, 1 and 2. Okay, so the voltage across this is actually, because this is grounded, this is 0 volt. So voltage across is also v pi. Therefore, you have two components. One is current going down. This is gm v pi. And the current coming over is j omega c mu over v pi. The reason why it's v pi is because voltage across VBC is v pi because shorted it to ground. Okay? So this is ground. And if you look at the input terminal, let's look at the input terminal. So if you look at I in, it will be determined by v pi divided by its resistance. So the resistance, there's two components. There's R pi in parallel, two capacitance in parallel. So it's R pi in parallel with j omega c pi plus c mu. The reason why they're in parallel because I shorted the output. So this is ground, this is ground. Okay? So you can do some rearrangement, and then we could simply do I out. Okay. So effectively, I out will simply be so we'll want to find out, remember we're going back to the current gain. So it's called the short circuit So your short circuit current gain should be define AIS, I out, I in under this test condition, which will be approximately, in this term, because we're assuming that C mu is much, much smaller. C mu is much more smaller than C pi. So we can sort of ignore this feed-forward component at the beginning first. Let's do this first. So then this component will be gm v pi. You ignore the feed-forward component. And the bottom term will simply be v pi. This can be rearranged. Let me use this. R pi. You do some rearrangement to find out this will be, let me write it down here. This is v pi. It will be R pi 1 plus. We do some rearrangement. C pi plus C mu R pi. We do some rearrangement, it will look something like that. And then this can be flipped at the bottom, 1 plus j omega C pi plus C mu R pi. Okay? And then we could cancel the v pi term. And then after some rearrangement, it will be gm R pi 1 plus j omega c pi plus c mu r pi. Okay? So what is GMV pi? GMV pi will simply be, if you, let me get this. GMV pi will simply be beta. Okay? So you can rearrange this as beta 1 plus j omega 0. We actually have a pole or a corner frequency of omega 0. So let me rearrange this. So your short circuit current gain as a function of frequency will then be rewritten as beta 1 plus j omega 0, where omega 0 is r pi, rc. So the r is r pi, c is c pi plus c mu over 1. Okay? Then we could find out what is omega t. By definition, AIS at omega t, which omega t is 2 pi, the transit frequency. Okay? So at omega t, by definition, this should equals to 1. At omega t, fall to unity. Remember, when does it fall to unity? Should be, so you simply enter beta 1 plus j omega 0. The absolute value should add omega t. Let me highlight this. Add omega t. This should equals to 0. So this is beta square root 1 plus omega t omega 0. Okay? So you can either do this by solving this equation, or we can do some approximation. We can do the Bode plot, and then we can do approximation as well. So if this is beta, it's current gain, we know that this is a short circuit current gain as a function of frequency. So we know that its corner is omega 0, and it will start to fall at a rate of minus 20 dB per decade. So as I said, minus 20 dB simply means that it's at a rate of 1 over 1. So this distance is the same as this distance. So falls to 1, meaning that the ratio between the two, so this is, if the ratio is beta over 1, omega, so the height between the two is beta over 1, then omega t over omega is approximately, based on Bode approximation, will be beta. That is to say, omega t is beta times omega 0, because it falls at a rate of 20 dB per decade. Okay? We can also do that through this math. So if we know that omega t over omega 0 is much, much larger than 1, this is typically true because we have relatively high beta. So this will become, this term, beta over, this will come out, will be omega t over omega 0. This will be approximately this, I should say. AIS will be approximately this. This equals to 1, where omega t is beta times omega 0. So this is the same from Bode-Plar or simply by the approximation based on your transfer function. Okay? So if you go back and look at what should, so we highlight what is omega 0 again. Omega 0 determined by r pi c pi plus c mu over 1. Okay? And omega t is beta times that. Let me write it down. It's beta omega 0, which is, if you do beta r pi c mu, and we know that beta is gm r pi. So you cancel the r pi, then it'd be gm c pi c plus, should be plus. Okay? So this will then give us a sense as to when does it, so as I said, when frequency passes, what is the maximum frequency is when two things compete to each other. One is the parasitic component, which will introduce a transconductance, or the parasitic component, the active device. So at a particular frequency, at this particular frequency, your parasitic capacitor transconductance or the conductance of the parasitic capacitance exceed that of the active device, the ratio. Active device, then you would then exceed. You would then no longer see the effect of the transistor. So the transistor is being shielded by this parasitic effect. Okay, so it's a competition between the two. One is the conductance. So it's a comparison at this particular, at omega t times c pi c mu. This is the impedance or conductance. If you think about it, it's a conductance of the parasitic component compared to that to GM. That's the conductance that's being induced by transistor, the modulation of the transistor. So once it becomes comparable or even larger, past omega t, this will be larger than that. So you compare, let me do this. So what happens is that when frequency exceeds omega t, the amount of current that's uncontrollable is not, it's for charging your parasitic component has become larger than that. It's being controlled by the transistor. Then there no longer be transistor effect, or your current gain will be degraded down. That means that you need more to charge up the device than what you gain by a transconductance. Okay? Okay, so let me stop here. So we're gonna probably don't have time to discuss the counterpart on MOSFET transistors. But we're going to come back on Thursdays and talk about that. And also remember to prepare for quiz, the last quiz, quiz number 6, which will start 11:30 on Thursday. It will be mainly on differential pair. Okay? Okay, so okay, that's it. I'll see you on Thursday then.